All right. Hi, everyone. Welcome to today's discussion. Um, Today we'll be talking about some more about trees, specifically balanced trees. Hopefully, you guys may have seen some of that in your project, but anyway, today we have a AVL tree. So I guess let's go ahead and get started on today's discussion. Just let me share my screen here. Just a second. Okay, here we go. Slideshow from me. Okay, so we're talking about balanced trees. So the difference between a balanced tree and just like a regular tree is, well, a balanced tree is balanced. Okay, but what does that mean? Well, it means that we like know something about the tree. Like we know that specifically the tree is, we know something about the height of the tree across nodes, right? Like there's some constant factor, constant multiple, or not constant, like constant factor, or just like constant that differs between the left and right tree for each sector. But okay, we'll get into like more detail. But okay, for today, we're gonna do a quick project review. We're gonna talk about the trees, basically 3 kinds of balanced trees specifically. And then we're gonna do a coding question. Okay. So for the Gator AVL project, so as you may know, the goal is to implement a custom AVL tree to organize UF student accounts based on Gator IDs. So the methods that will be called are insertion, remove, search, and traversals. So for traversals, those are like what we talked about last week: pre-order, in-order, post-order. Search is just like finding something in a binary tree, because ultimately an AVL tree has more to it than a simple binary search tree, but it's still a binary search tree, so searching will be the same. And removing is similar too, in that you're removing just like how you would with any other kind of binary tree, where you get the in-order successor, in-order predecessor, and replace the node. And insertion, the difference between this and like regular tree that we would, well, okay, for this project specifically, like that's how a remove would be. And then for insertion, you need to be aware of rotations. Okay. So yeah. So steps for this project, you're designing interface, modules, and functions, and then you parse the input and ensure that the constraints are met. And then you need to build the main function to parse the inputs. So you have your main function, which just takes an input, parses it, and then you call your functions. You have like your tree, and then you call the functions for the tree, and you have to test your code like that. So those are the main steps. It's a tree. If you read the directions for it, hopefully we kind of be able to questions. Just message me or send a message in Slack or message Joshua. Yeah. So the grading for this, there are 5 test cases and then 10 hidden test cases. That's 75 points. 15 points for documentation. Talk about the computational complexity of each of the methods. Then your reflection for that, and yeah, then code style and design. So modularity means like have code, like don't put everything in one method, right? Like split things in one method if it makes sense. Comments, white space, like don't put everything in like a 1 line of code. Naming conventions. Hopefully, I guess it's kind of self-explanatory. And then bonus, you can only get up to 100 on the exam, but or not on the exam, on the project. But yeah, if you want to use the catch framework, yeah, it's a bonus. Okay. So you might be thinking to yourself, why would we use a balanced tree as opposed to just a regular binary tree? And the reason is that for a balanced tree, it has some nice things about it, right? For the computational complexity, because we know that like with a regular binary search tree, like a tree like this is entirely possible, right? This is a valid binary search tree as long as the nodes are valid. So I could have like, I don't know, 1, 2, 3, 4, perfectly valid. But it kind of defeats the whole purpose of a binary tree, because this is just a linked list in essence, right? Like it's no different than a linked list. The reason why we use binary tree is that we can kind of like cut out like the number of things you actually have to check. Like ideally we'd have maybe something like this would be better, right? We rearrange the tree to maybe have like, if there's 1, 2, 3, 4, maybe like 2, 3, 4, and then 1 here, right? And that way we don't have to check everything. We can check log n because at each level, right, we make, at each level we make, I was thinking about this. Yeah, at each level we make 2 splits, right? So we can kind of think about it, right? We have our root, right? And each of the subtrees has its root, which is basically the same. So we can kind of recurse split things. But we're just going to consider the main root. And the nice thing is that if it's perfectly balanced, right, we know that there are n things in the tree, right? So there are n things in the tree. And because it's a binary tree, right? Like if it's perfect, then we're gonna have 1 at the first level, 2, 4, right? And so on, right? Then how many things do we actually have? Well, if we sum them up, we kind of talked about this last week, right? How many things are in the tree? Well, it's 2h to the h minus 1 are in the tree, right? And if the height of the tree is h, right, then how many things we have to check in order to like search to find an element? Well, we only have to go, each time we make a comparison, we go down a level. Well, h in this case, right, this is equal to the total number of things in the tree. So what is h? Well, it's just log n, right? It's log base 2 of n. I mean, 1 is like constant factor, you don't have to worry about it. So basically it's something along the lines of 2 to the h equals n, right, for a perfectly balanced tree. So then we have log n is equal to h. So to find anything in the tree is log n. To insert something, again, like to find where it goes, we have to go just like h, right? So insertion and deletion is the same thing. So that's really, really nice about balanced trees. But again, for regular binary search trees, that doesn't work, right? We might have to check everything. It might be like a linked list. So that hopefully that gives you some idea of why we want balanced trees. Okay, yeah, so regular search trees, binary search trees, they have average time complexity of log n, but it's possible that it won't be, right? It's possible that we can have something really, really bad. Yeah, and this will never happen in balanced trees, which is why we use them. So what's a balance? So we usually use balance factors, right? And a balance is the height of the left subtree minus height of the right subtree, right? So in this one here, right, the bottom left image, it's 0 minus 6, and the right image is 2 minus 2. And interestingly, it's also important that we check, or like one thing we can also check, right, is the actual internal nodes. So like 0, 0, 0, 2, right, also has balance factor 0 because it's 1 minus 1. And 0, 0, 0, 6 has 1 minus 1 as well. So also 0, right? So the balance factor is called the balance factor. I know, shocking, right? So you take a node, get the height of both its left and right subtrees, subtract the height of one subtree from another, and you can do that for height of left minus right. You can also do vice versa because ultimately the absolute value is what we care about, right? Because it's unbound. Like if I have like 4 more on the right, 4 more on the left, like it's ultimately the same. Like we measure it differently because you do left minus right, but you can do right minus left, and you'd have the same information. Yeah. Yeah. And these slides in general, we're just gonna do left minus right. But again, like if you want to implement your own code, right minus left, like that's perfectly okay. Right. It'll work. Okay. So insert balanced binary search trees. Searching average time complexity is log n. Worst case time complexity is also log n, which is nice, right? Because as opposed to before, where we had backwards. Oh, okay. Well, I guess I talked about balanced trees here, but the average time complexity for searching, insertion, deletion for regular ones is log n, but the worst case is O(n). But here we have worst case and average are both log n, right? Which is nice. And I already kind of showed you why. We can talk about this. Every node has another way of thinking about it, actually. So like I proved it one way, but like there's another way of looking at it, which is that every node in a balanced binary search tree has balance factor is -1, 0, 1, and it's the difference between the height of the left and the height of the right. Right. So it ensures that you always have the minimum number of nodes to get to the target. And if we think about the branching structure, right, you have 2 at each level, right? You're splitting it up into 2. So you have basically the total number of nodes in the tree, right? Divided by 2, divided by 2, divided by 2. How many times do you divide by 2? However many times it takes to get down to where you need to go. So it's going to indicate that we're only going logarithmic, right? Okay. So worst case here for unbalance is 7, right? And that's a lot more. Worst case for balanced here is 3, right? And so balanced trees tend to be pretty good. Unfortunately, that means it's a little more work for us. We have to program things. So for example, we have to rotate, right? So in order to make a tree balanced, you have to do rotations. So there are 4 types of rotations based on the imbalance and the limit of the nodes. So it's left, right, left, comma, right, comma, left, right, and then comma, right, left. Those are our 4 types. And okay, let's talk about that. So left and right rotations are like, I guess, the simple ones. The other one's a little more difficult, but let's start with left, right, left and right rotations. So how I like to think of it is like, I like to think of it like 3D. So like you have 0, 1, 2, like 1, 2, and 3, right? So I like to think of it like you have balls on a string or something, or like, I don't know, and they're like this. And then you just, okay, I want to pick up the middle one. So pick up the middle one, and you're like, okay, now I'm holding the middle one. And like, I don't know, gravity does the rest. And so like, you're like, yeah, okay, I want 2 in the middle. And like, you hold it, and now 1 goes to the left, and 3 is on the right. So you just think about like picking it up. That's how I think of it. And notice that balances it, right? Now the balance factor of 2 is all of a sudden 0 because left is right. Left is 1, right is 1, 1 minus 1, 0. And for this case, it's actually not that, right? Because we have right is 2 and left is 0. So that's not good. And then for left case, it's similar. I think of it kind of picking it up. And again, we'll have the same exact tree that we get to. But this is the right rotation. The right rotation is just like taking the left, like the one that's imbalanced. In this case, 3 is not balanced, right? And so we take its left child and we make 3, right? We take 3 and the 3, we're going to specifically take the 3 and move it to be the right child of 2. And 1 will remain just the left child of 2. So we're really only changing one thing here. Okay. Like we don't have to move the 1, right? But we do have to move. I mean, it's the opposite in the left, in the right, right. Okay, so let's see a little more. So left right rotation is a little more difficult to see. So yeah, for this one, what we want to do, well, do we have a problem? Yeah, because still we have left. The height of left is like 2 and the height of the right is 0, and that's imbalanced, right? So we have 2 steps. 1, we have to duration to get us in this format, which is a left. We get ourselves into left, right? And then from there, we get ourselves in the balance case. And the way we do that, right, is we do a right rotation. Because the left or right rotation is just the right rotation followed by left. So if you think about this one, what we're doing on this, if we have left to right, we need to do a left right rotation, which is a right rotation followed by a left rotation. So really there are only 2 kinds of rotation, but you need to do 2 at once for 2 of the types of imbalances. So left right, you need to do a right followed by left. And you can see it's left right because it's left and then right. I mean, there you go. And right left is similar, but the opposite. So it's not similar at all. So yeah, if you have right, left, right, it's right, left. So we do a left rotation followed by a right rotation. You get the same thing, right? And it's right, left because it's right and left. Right, left. It's kind of easy rotation. So if the parent, right, when we insert something, for example, for our party gets insert, but maybe, okay, yeah, for our party gets insert. So the balance factor for the parent, right, is +2, and the child is +1, right? Then we know, right, that what that means is that we're gonna have something like this. The only reason why we have B +2 on the parent is we have more on the right, right? So it's gonna have to look like this. We're gonna have something on the right, but the child's also +1. So it means I have more on the right than on the left. So we're gonna have something like this. And so +2 and +1 implies we need a right rotation because it's gonna look like this. Oh, sorry. It's left minus right. So I was saying actually right, which is a left rotation. So sorry, I said it backwards. Yeah, but for -2 and -1, it would be like this, right? So it's left, so we need a right rotation, right? So the reason why I call it that is because we're basically rotating right. And a left right rotation, if it's +2, right, we have more on the left. So we know our next one's on the left. Well, the child is -1, which means that it has more on the right than on the left. So it's going to look like this, right? And then right, left is similar, right? We have -2, and it's more on the right. But then the child is +1, so let's go left, right? So this is what we have. Okay. And yeah, I actually, as you noticed, like when I first saw the slide, I didn't read the bottom, because I was doing height of right mass. But anyway, yeah, just for this discussion, that's what we're reading. Height of left minus height of right. Okay. Yeah. So question, for the left subtree 4, 6, and 8, what imbalance is it? And what rotation is going to fix it? So you can pause and answer. Okay, so let's answer this question. So we notice that we have to go, oh, the problem is, right? 8 has left minus right, 2. And 6, left minus right, 1. I also notice, maybe even simpler because we can actually see it, is it's left followed by left, and 8 has nothing on its right. So it's a left, right? What rotation will fix it? Well, what rotation fixes a left, a right rotation, right? And we can look at the balance factors, and that kind of tells us that. So we can either go by the balance factors and follow this, or if we can actually see it, maybe it's also kind of easy to see, right? Okay, so right rotation. So performing the rotation is going to look like this, right? Kind of just like pick up the 6, then the 8 moves down, and the 4 moves to the left. But remember that 8's parent, right, is also 8's parent's child, which was 8, right, is now going to become 6, right? Because 6 like moves up, and then 8 moves down. So yeah, we're basically like switching their places and then like picking it up, right? Picking up the 6. Okay, so for this one, what kind of imbalance is it? Well, okay, you can pause and answer if you want. Okay, so if you unpaused, as you may notice, right, this is nothing on the right of this one, but we go left and go right, right? So what kind of imbalance is it? It's a left, right. And the type of rotation is also left, right, which means we have to do 2 kind of rotation, right? And the first rotation is to get it into a left form. And then we have to actually balance it, right? Because for left, right, and right, left, there are 2 rotations in a row we have to perform. And then it's balanced. And so yeah, as you can see, there are like a couple steps to go through, but we can even go back, right? And see that this case, right, because it was left, right, it was left, right. Yeah, it was left, right. So for left, right, parent was +2, which we had -1, right? So we left, right. Okay. So what rotations does this tree need? Well, here we can check each of them. Go ahead and pause. Okay, so I guess you got to pause, or if you haven't, you skipped ahead to here. So then I don't know how that works, but okay, whatever. Anyway, so yeah, here is 10. What's the balance factor of 10? It's 0, right? Left minus right, 0. 5. Left minus right, 1. 17. Left minus right is -1. So does it need anything? The answer to that is no, it doesn't. Right? It's already balanced because we don't have any like any balance factors of absolute value. Like, so no balance need to be done. How about this one? All right, you can pause. Okay, and now it's time to answer, I guess. So yeah, what do we need to do? A and B. So as we notice, A, right, is 17, right, has balance factor of left minus right, -2. And it's a right followed by left. So right and then left. So right, left, right. How about B? Well, it's a right and then right. So we need to do our left rotation for B and our right left rotation for A. So yeah, A is right left and B is left, right? Okay, cool. All right, so how about this question? What's the worst case time complexity we're inserting into this tree? Okay, so now we can answer, right? So yeah, you could have paused and just okay, well, time's up. If you didn't pause that, you can still pause now, I guess. I can't stop you, but like, it'll make a lot of sense now. Which I guess would sound weird if you already paused it, but like, okay, back to this. So yeah, the problem is this tree balanced? It's not, right? Because it's basically a linked list. It just functions as a linked list. Like it's a tree structure, but it doesn't need to be. So what's time complexity of like inserting into linked list? ON, right? And because this tree is imbalanced, for an unbalanced tree, the worst case time complexity for inserting into an unbalanced tree is ON. So that's exactly what we have here. You have to iterate through all of them. So that's the worst case time complexity, right? Yeah, and for searching and deletion, it's going to be the same for unbalanced tree because you have to go possibly through everything. And that's pretty bad. Okay, what is the worst case complexity of searching in this binary tree? All right, pause and okay. So the answer is, well, we can answer it this way. Is it balanced? It is, right? So what's the worst case? Log n, right? And yeah, in a balanced tree, the worst case complexity of basically every operation is log n. And for an unbalanced one, the worst case operation is pretty much always n. So that I guess that can help. But like, even, yeah, anytime you have to visit every element, it's gonna be one. But here, like for searching, we obviously don't have to search every element, right? Because we can decide, like, let's say I want to find the 3, right? Well, I know it's greater than 2, so I go here. And I know it's less than 4, so I go here. And notice at each level, you're only searching one thing. And if the height of the tree, as we said before, is just log n, then you only have to get through log n elements, right? Hopefully that makes sense. So AVL trees are a special kind of balanced binary tree, right? And this is what you're doing for your project, basically. Is yeah, self-sustaining or self-balancing, self-balancing, yeah. But like it sustains the balanced property. So okay, anyway. Yeah, so every node has a height or balance attribute, which may be updated in an insertion or deletion. Okay, yeah. So basically in an insertion deletion, right, we're basically balancing again. I think for your project you'll have to do an insertion, but in general, the AVL tree, you do it on insertion or deletion. Well, yeah, I might be wrong. I think I'm right though. Okay. After each insertion or deletion, at most log n nodes are reduced. So what that means is that that's really good, right? Because if this weren't true, right, then ultimately insertion or deletion might still be ON because our update might be really bad. But thankfully for AVL trees, it's not. We only have to update like along the path of the for the tree of the thing we updated, which makes sense, right? Because we only updated the balance factors along our path, right? To the thing we removed or to the thing we inserted. So obviously, you know, the number of things on that path is log n because the height of the tree is log n. So that's kind of why. Yeah, that's the number of things we actually have to update for the height balance factor attribute or rotate, right? So yeah, we update in insertion and deletion. And those are the times we actually update, right? And because the state's balanced and the amount of time to actually update is only log n, and the amount of time to find, like to insert and delete is log n as partly as a result of that, right? Then all of its operations remain log n, right? Because if it only takes log n to insert and delete, then of course it only takes log n to search. So that's really nice, right? Having a tree which ensures they always have log n for every operation. It's really helpful. Yeah. So we can see kind of how it adjusts itself. So its original tree, we insert the 5. Oh no, it's unbalanced. And it's unbalanced to 3. So it's right, so we need to do a left rotation. That's exactly what's done here. Yep. Yes, so it goes, tree iterates through the nodes, it passes through, right? Because you only have to go along the path, because that's the only time we're ever going to have a problem. So we go along the path to see where there's an imbalance, if there is one. And if there is, right, it just performs a left rotation. And then, yeah, once we've updated it, we're good. Okay. So red-black trees actually are pretty interesting. In C++, actually, believe it or not, map, like the ordered map in C++, actually uses red-black trees, which is kind of interesting. Red-black trees are really, really nice to use. And yeah, the reason why they're used for ordered maps is because they're really good. They tend to be, in performance-wise, a little better than AVL trees because the update doesn't take as long. And that's one nice thing about them. Oh yeah, actually it's here. It's math class. Ooh, I got it right. I'm just kidding. But yeah, it's used in scheduling algorithms or just in general. It's really good for trees, but it is a lot harder to write code for them. I remember like, okay, actually, yeah. Another interesting thing is one of the other trees we'll talk about later uses red-black trees. So yeah, it's kind of interesting. Oh, we'll talk about when we get there. A binary tree, yeah, it's a binary tree that searches the balances itself by following these 4 rules. A node is either red or black. Yes, these 4 rules I guess are good to know. A node is always one of 2 things. It's always red or always black, so only 2 colors. And the root is always black. And a red node has black children. So what that ensures is that we never have like 2 red nodes in a row, right? Because if you have a red node, if it has children, they're black. And the number of black nodes in any path to the root from root to leaf is the same. So if I have like this one, right? And what's the question in a second? I don't know why it's skipped ahead, but if I have this one, right, or this path, right, it doesn't matter. Along both paths, I'm expecting the same number of black nodes, right? Okay. So which of the following is true about a red-black tree? So you can probably answer. And I think I know which one it's not, right? I'm sure you all know. Okay. So the answer is obviously not this one. But yeah, it's a node is always red or black, and there are black nodes in a path of their to the same. Okay. And this one is not true. It's if a node is red, its children is black, and then, or yeah, and then the root is always black, not right. So we can talk about splay trees, and splay trees are also kind of interesting because splay trees are like they're trees that always rearrange themselves. So like the most recently visited element is the new root. And the reason why is because if you think about it, right, if we're trying to search for something, right? Well, splay trees are also a balanced binary search tree. So they're useful in the sense that they're balanced, but also that like the root takes the least amount of time to visit, right? Because you don't have to actually go through the whole tree. Just it's the first element, right? So the nice thing about splay trees is that like the most recently visited element is going to be really high up in the tree, which is useful if you think about it, right? Because that for like caching, right? I don't know if maybe you don't know what cache is, but if you want to like get something recent, right? Like a lot of times in a lot of systems, the things that you use most recently are most likely to be used again. It's possible anyway, right? So splay trees provide a nice way to do that because the most recent element is a lot faster to get to. So that's good. But okay, they're also self-balancing binary search trees. After a node is accessed, it's moved to the root via zigzag rotation. So keep doing rotations until it gets back to the root. So in this case, we visit the 1, and so it has to move all the way up the tree until it gets to the root, right? Yeah, and it ensures that the most commonly accessed nodes have least access time because, yeah, the most recent access is going to be at the top of the tree, and near the top of the tree is anything you've recently accessed. And if you keep accessing things, then they're going to be near the top, right? And so they're going to take less time to access, which is really nice. Okay, B trees. So this is actually exactly what I was going to say. What I was talking about earlier with red black trees. So B trees internally make use of red black trees. Each of these little nodes here, and I don't think you need to know this, but it's kind of interesting, or one way to do it. They don't actually, you don't necessarily need red black trees, but in general they do use red black trees because each of these, right, has to be sorted in some way. So if you want like a tree, right? Well, we'll get into the details, but like in general, a lot of times for implementation wise, which you don't really have to worry about, I just figured to mention it. A lot of times is with red black trees. Okay. Unless it says it here. I don't remember. I don't think it is. Okay. Trees are self-balancing binary trees. But yeah, they're designed to store huge amounts of data for fast query and retrieval. So a lot of times you need to get things from memory, right? Maybe you have to get things from memory, and like let's say get an array. Well, it doesn't make sense for you to like just get a simple array, because if you do that, or you only get one element from the array. Like it doesn't make sense to just get one element, because if you're accessing one element of the array, it's likely you're accessing like the one next to it, for example. So B trees are nice to like load in a block of memory. So it stores huge amounts of memory for fast query retrieval. So you might get a block, which is nice because you can get to the whole block much faster. Because if it's closer, right, you load it in to the tree, like, okay, yeah. All right, anyway. So they can have multiple key value pairs in a node, and they're sorted ascendingly by keys. Yep. And so that's kind of what we see here, right? And it's an n-ary tree, so it may not be a binary tree actually. I think I might have said self-balancing binary tree. That was a mistake. It's just an n-ary tree, and oftentimes it's not a binary tree at all. And internally, yeah, there are other kinds of trees that help organize it. But that's an n-ary tree, and there are a couple of important properties. So all nodes have at most n children. It's an n-ary tree, so of course that's true, right? Yeah. The root is a leaf or it's not a leaf, right? And if it's not a leaf, it has either 2 children or anything up to n children. Internal or non-leaf nodes have at most, oh sorry, not at most, they have at least, at most n children, of course, but they have at least ceiling of n over 2 children, because of the way B trees work is if it's any, it's more than n, it's actually going to do a split. And when it splits, the interesting thing about a B tree is when it splits, it actually like, or okay, like it'll try and combine nodes so that they never have less than ceiling or 2. But if it has to, like has more, then it'll split, and then n plus 1 divided by 2 is like, guaranteed to be at least ceiling 2, right? Okay. But non-leaf or internal nodes have a maximum of n minus 1 keys. And L is the maximum number of keys that items the node can have, which is some other thing we have. So B trees are interesting, and B plus trees are also interesting. So like I remember last semester I had a project for one of my courses, which was really hard, which I had to make a B plus tree. And I ended up just using a map for my internal nodes because making my own red black tree was like a lot of work too. But okay, that's you know how it is. B plus trees are basically, they're just B trees. The only difference is that B plus trees have a linked list in their have a linked list in their leaves. Because and another thing about a B plus tree that's interesting is it doesn't actually, all the data is stored in the leaves. So if you want to access all the data, you can actually go through that linked list. Whereas B tree, the data is stored internally and at the leaf level, but for B plus tree, it's only at the leaf level you have actual data. Okay. So data is stored, yeah, so the differences are, like I said, where the data is stored. Searching can be a bit slower in B trees because it's stored internal in leaves. Yeah, in B plus trees, it's interesting because like the search keys, because they're not actually part of it. They're just the search keys. The redundant search keys might not be present, or they may be present, right? You might have multiple search keys, and that search key may not even be in the tree because I never removed it by that time. And there are no redundant search keys. in B tree, like everything is only there once, right? Deletion is really complex for B tree. And for B plus tree, it's a lot easier because you only have to remove it from, like, okay, you have to remove from linked list. It's not like super trivial, but it's a lot easier. And leaf nodes can't be linked together, but they are linked together. So those are kind of differences. Yeah, the distinctions are each node contains only keys, not pairs. And then all data is stored in nodes. Okay. And then additional level is at the bottom with link. Okay. So yeah, I know there's a lot about trees. Okay. But anyway, like we said, the reason why I might want to use these for being the plus trees. Why this one too? Well, yeah, it allows us to get like external blocks in, right? So like a cache block. So in your cache, right? Again, caching is often used for getting like data. So if you know that you just got data from an array, right? It's likely you'll need other data from that same array. So maybe you want to store the whole thing, the whole array in your cache block. So it's all like easy to access memory and together. So it's not, you don't have to access like every element. Oh, I want to get that one. I want to get that one. Because then it just ends up acting like a linked list, which is not the point of memory. So an array should be contiguous block memory, which it is, but if you have to like go and get them from different places, maybe it's performance like this. So maybe not. But okay. So what are the applications of B and B plus trees? Yeah, indexing file systems and databases is definitely an application, right? So if we're presented with a completely full B plus tree with n equals 3 and L equals 3 and height equals 2, how many unique keys are there? So pause and try to answer. And we can use these to advantage. Okay, so let's go over this. So we have 27. And the reason why it's 27, right, is we actually make use of these, right? So at level 1 or level 0, right, there's just one node, which will have 2 values. And the reason why it has 2 values is because this is an internal node, right? And non-leaf nodes, so internal nodes, have up to n minus 1 keys, right? And we know it's completely full, right? Because it says it. So if it's completely full, we have 2 at the rear. And then it's completely full, so its height is 3. So, and L is 3. So it has 3, this one that has 2 has 3 children, each of which have 2, right? But at the next level, we aren't restricted in the same way, right? Because it's a leaf. So we don't have n minus 1, we have n. So 1, 2, 3. And each of these have 3. So 3, 6, 9. And then we have 12, 15, 17. What? 12, 15, 18. My goodness. Can't edit that. Okay, and then, okay, 1, 2, 3. I'll draw up there. And then 21, 24, 27. But because of the plus tree, how many unique keys are there? Remember, keys are only stored in the leaves. So don't actually worry about this in internal. So only we're at 27 rather than adding on the other 8, which would be 35, but that's not even against choice. Okay. Hopefully that makes sense. So we can kind of see it. There are 2. And each of those have 2, right? Because n minus 1. And then, yeah, 3, 3, 3, 3, 3, and 3, 3, 3. And it's only that way because we said completely full. Right? Otherwise, we wouldn't be able to answer the question, so we wouldn't know how many are each. Be like, oh, what? I don't know how to answer the question. We're like, yeah, because it doesn't have an answer. Okay. Okay. So if we're given a paired binary tree, there's no pointer looks like this, right? Next pointer is curious. We want to connect each pointer's next value to the node it's right, like below. So I want to write a way to make this modification to the tree. And to actually do this, right, you might want to think about like, okay, how can we approach this problem? Well, maybe if we're given the binary tree, maybe this has some sort of relation with, well, actually, instead of saying that, let's just kind of like work through it on pen and paper before I like get to what it might be related to. then you can maybe figure it out for yourself. So if we look at the first node, right, it's a 1, and its next pointer is null, right? And so at what point do we get to the null? Well, we get to the null, right, after we've gone through everything at this one, right? So, all right, so what are we connecting together? Well, we'd say we're connecting together this level, and we connect together this level, and we add null, right? We get a null when we've gone through everything in this level, right? So if at any point, like I say something, oh yeah, I think I can try and figure this out for myself, you can totally try and go ahead and do that, right? So maybe that makes sense, but if it doesn't yet, that's okay. So notice that we kind of get to this null, right? After going through everything is level, right? And we're connecting together everything in the level one by one, right? So maybe you kind of see, I don't know, what this might be related to, right? Which is that we're going level by level, and we're connecting together like the next thing within that level and the previous thing in that level, right? And so what might this be related to? And so maybe you can pause and think about it if you haven't already written the code. But okay, maybe not. It's okay. So maybe if you don't know, we can go over it. So actually, for this one, right, what we actually notice is that it's related to in-order traversals, right? Or not in order, sorry, not in order at all. Level order, sorry, sometimes, just like before with the 17, it's 15 plus 3, silly me. But no, it's level order, right? Because at each level, right, we're looking at it, we're like, okay, so this one's next at this level is null. The next of the 2 is 3, and then next is null. So we kind of see this as like almost a level order traversal, right? Except there's a little bit of a twist, right? It's almost exactly the same. The difference is that we actually need to connect this one with the next one. But that's okay, because if you also think about it, the way we do a level order traversal is we use a queue, right? Use a queue. When we add things to the queue, right? Maybe you see where this is going. And if you do, and you haven't already written the code, maybe go ahead and do that. But when we add things to the queue, right? Then the next thing in the queue, right, is the next node that we want to look at, because we go left, right, and then right. But then we go left and right on the left child, and then we go left and right on the right child. So really, the first node that we're going to look at from our queue, if we look at just the queue, actually, let's do that. We have the 1, then the next thing that actually goes in our queue and we look at is the 2, and the 3, and then the 4, and then the 5, and the 6, and the 7 in this case. So also what we notice is that we can just connect, we can like store the previous node and then make a pointer to it, to the next node in our level order traversal, right? And until we reach the end of that level, which is related to your last STEPIC assignment, in which you had to know the sum at each level. Well, you only knew the sum at each level when you finish that level. It's similar here, because when you finish the level, instead of like computing the sum, you just set the last ones next to null. So if you're able to do the previous STEPIC quiz, then this one is actually really similar. The difference is instead of like computing a sum, you just have to like store the previous node and make its next, the next node in the queue. So yeah, that makes sense. And I think we'll go over the code. I don't know if I'm going to write out the code. If it's here, we'll just kind of go over it a little bit. But interestingly, yeah, it's very closely related. Yeah. So as I said, right, we're just going to go through it exactly like how we discussed, right? And oh yeah, if you want to write the code now, you haven't seen it, like you haven't really looked through it yet, you can go ahead and do that. But otherwise, like, we'll go over it. So the idea is using a level order traversal, right? And again, the trick is we're setting the current pointers next to null pointer if I is at like count -1, and if not, we set the curve's next value to the thing at the front of the queue. So basically, as you go through the queue, right, it's exactly like what we just talked about. But let's actually just walk through the code, right? If count is 0, if the root is null, or not null, sorry, we push the root, right? And while it's not empty, this is how we do a level or traversal, and it's exactly the level or traversal here. The only difference is that we actually put a for loop in it. We put the for loop in our while loop, so that way we're doing things at each level, count as keyed out size. And the difference is actually at the end, right? Which, oopsies, is that if I is equal to count -1, right? We make the next pointer equal to the next traverse. So yeah, we're just setting it to no pointer. Otherwise, like if we're not done, we're setting it to keyed up front. And yeah, if current left is not null, then we're going to push that and we're going to push that. And that's pretty much it. Like this is exactly like what you had for your last topic, except with a couple of modifications to allow us to set the next pointers. Hopefully that makes sense. If it doesn't make sense, of course you can always message me or Joshua or in Slack or whatever. So yeah, that goes over the solution. All right, if you have any questions, which nobody answered a question. Oh, Andrew, I have a question. What's that, Andrew? Oh, I forgot. Okay, well, if you remember, Andrew. Yeah, I don't know. It's been a long time. But okay, yeah, if you guys have any questions, feel free to reach out, like I said. And that's about it, I think. Okay, yeah, sorry. So I guess it's not about it. The resources are listed here. And for visualizations, these are kind of nice, I think. They help you like visualize what's happening as you go through it or as you do things. So it's kind of nice. And don't forget your quiz due. And that's actually it. So thanks for listening today. And yeah, have a nice day, I guess. As I said, thanks for listening. Bye, everyone. Yeah, okay, bye.